Now that we've discussed Chapter 10.1, which is relationships between heat and work, and we've gone over the first law of thermodynamics, I'm moving on to Chapter 10.3, which is the second law of thermodynamics. We've previously discussed heat engines, where the net work is equal to heat input, which I'll call Q sub H, minus the heat output, which is Q sub C. However, it is impossible to construct a machine that does exactly equal work to the energy absorbed. So let's take a look at how that works. The second law of thermodynamics states that no cyclic process in which heat is converted entirely into work is possible. Instead, we measure exactly how efficient a machine is by dividing the net work done by the quantity added as heat. And we know that this net work equals quantity added as heat minus energy lost, and then we're dividing that again by heat. So we can simplify this to say that the efficiency of the machine is equal to 1 minus the energy removed as heat divided by energy added as heat. And 100% efficiency, as you can see, would only be possible if this numerator is equal to 0, which would mean that no energy is removed as heat, and that's just not possible in the real world. We define entropy as the measure of a system's disorder. In the real world, systems tend to move from order to disorder. So as I've drawn up here, we have this orderly system in which the two colors are divided, and then that moves to a state of greater disorder over time. Systems tend to go from order to disorder to maximum entropy, which is the maximum amount of disorder they could have. You could imagine shuffling a deck of cards, and as you shuffle more and more, they wouldn't go back to a state in which they're ordered by number. Instead, they would just become more disordered. This is why entropy increases in the universe. So according to the second law of thermodynamics, the amount of disorder of a system and its surroundings will never decrease. That's what I discussed on the last slide. But what also happens as a system reaches greater entropy is that it has less energy to do work. This is because there's more disorder in the system. So now that I've defined the second law of thermodynamics, we'll do some practice problems. Number 1. If an engine takes in 22,540 joules from the boiler and gives up 19,150 joules in exhaust, what is its efficiency? So I went over earlier that efficiency, which I'll call EFF, is equal to 1 minus the energy removed as heat divided by the energy added as heat. So we're solving for efficiency. We have this 1 in here, and then we know that it gives up 19,150 joules in exhaust, so that will go on the top. That's the energy lost as heat. And then on the bottom we have energy added as heat, which are the 22,540 joules it takes in from the boiler. If I simplify this fraction and then subtract it from 1, I get that the efficiency of the engine is equal to 0.1504, or in other words, about 15.04%. Number 2, this is a conceptual multiple choice question. Of the following, which is the best description of the second law of thermodynamics? So essentially we're just trying to define the law that we've just been learning about. A. The total energy of the universe is constant. Well, this relates most closely to the first law, so I'm going to cross that out right away. B. The efficiency of a heat engine can never be greater than 50%. Well, we never really learned that. We learned that it must be less than 100%, but there's no specific requirement about the engine being greater than 50%. So I'll get rid of that because it seems false. C. The amount of heat required to vaporize a liquid is greater than the heat required to melt a solid of the same substance. Well, this may be true, but that's not at all related to the second law of thermodynamics, which we were just learning about. So I'll get rid of that. D. The entropy of the universe is always increasing. Well, we did learn that entropy is increasing, so I won't eliminate that just yet. And then finally we have E. As the altitude increases, the boiling point of water decreases. Well, this is also true. However, we never learned about this in the unit about entropy in steam engines, so I'll get rid of it. We're left with choice D. The entropy of the universe is always increasing. This does define the second law of thermodynamics. Number 3. An engineer claims to have built an engine that takes in 7.5 times 10 to the 4th joules and expels 3.5 times 10 to the 4th joules of energy. What is the efficiency of the engine, and is this efficiency possible? So we have our equation where efficiency equals 1 minus the energy lost as heat divided by the energy added as heat. Now we can plug in the numbers we know. we have 1 minus, the energy lost is 3.5 times 10 to the 4th joules, and then on the bottom we have energy that it takes in as heat, so 7.5 times 10 to the 4th joules. Now if I simplify this, I get that the efficiency of the machine is 0.53. And the only requirement we know about efficiency is that it must be less than 100%. As you can see here, this value 53% is less than 100%, so this efficiency is possible. This has been the last section of Chapter 10 of Holt Physics. Thank you for watching.